Okay. Can anybody online hear me? Can you say anything? Someone? Nobody? It's still 12. Hello, 1, 2, 3. 1, 2, 3.
Hi, Professor Gonzalo. I can hear you. Yes.
Let's see. We cannot hear you, but it's probably a problem with the volume. Sí, al máximo. Pero creo que está funcionando bien acá. Marco Aurelio, ¿fue para la demás fuerza? Números.
Yes, I can hear you.
Okay. No problem with the audio here. Ponemos aquí. Aquí está la. Vale, es que para elegir el output, para que no sea en tu ordenador, sino que sea. Ciencias. ¿Dónde está el audio? Del Zoom, ¿verdad? Pero es que no me veo. Vale. Está aquí. Polygon. Okay, now, ahora, don't know what I'm speaking. Can you say something again?
Yes, I see you.
He cambiado el micrófono. Sí, el micrófono es importante cambiarlo, pero también el audio. He cambiado el micrófono. Ok. Speakers. Once again, say something.
So, good morning.
Good morning. It sounds, please continue saying things, numbers, 1, 2, 3, 4, 5.
1, 2, 3, 4, 5, 6, 7, 8.
Maybe volume, yeah. Just control it. Sí, ahora. Claro. Sí. Okay, so I don't know why that because they don't know the batteries are not working well. So pequeñitas. ¿Tienes? Let's try again. Can you say something? Now it works.
Yes, I can. 1, 2, 3, 4.
Very good. Now we can hear you. Thank you so much. Okay, very good. Thank you, Nestor, for the batteries. Okay, then now we can move and it works. Yes, now it's moving. You see, it's moving. It's looking for me. Yes. Okay, now it works. It was just the batteries. Okay, so welcome back. Only 4 minutes today. Yesterday there was a delay of 10 minutes. 4 only today. Tomorrow it will be on the clock. And our first speaker of today's session is Ángel Rincón. He did his PhD in Chile. a university with a long name, the Pontificia Universidad in Portuguese. And then he came to Spain, to the University of Valencia. University of Opava, doing our postdoc, and today we are honored having him here to tell us about his work on perturbations on.
Thank you, Gonzalo. And again, thank you for the opportunity to discuss about physics. Okay, so the idea is try to discuss something regarding regular black holes and motivated by the fact that we can also include certain properties. In this case, we try to include dark matter, like a more realistic effect, and study how certain black holes, in this case regular, responds against certain type of perturbation. So the idea, the main idea was developed in a recent paper, in the I-COOP paper, with these some colleagues from US and Chile. And in summary, the idea is try to mention why I consider black hole importance, why I believe that now we are in special scenario to investigate perturbations, different kind of perturbations in black holes, why regular black holes are also quite relevant in Einstein theory. Certain, well, the problem, the concrete problem that we are trying to improve, and a few properties that we will focus in this talk. That is, they are basically the so-called quasi-normal modes and the absorption introspection, which are two properties of the physical of wave. Okay, and after that, the take-home message. Okay, first, let me start by the very beginning, which is why I consider that black holes are important. Okay, in general, black holes are one of the more trivial prediction of Einstein theory, and that is, well, that is because mathematically they are in principle quite simple, and the reason is because you can also describe a significant amount of black holes by a few constants in general, usually for the black hole mass, for the angular momentum, and in the scenario that you can find some black hole with charge with the electric charge. So you in general can describe a black hole with only these three parameters plus extra parameters from some exotic theory. And in general, black holes are relevant because you are studying the strong regime field, the strong field regime. So you can try to extract information or learn about certain kind of physics in the strong field regime. And also, black holes are quite important because, as I mentioned a few seconds ago, they are simple solution of the Einstein or modified Einstein field equation, which means that not only in classical but also in modified or quantum-inspired theory of gravity, you can find certain black hole solutions. We have many other motivations to investigate black hole, but that's just a few ideas to keep in mind and to justify why black holes are important. Okay. In general, the idea is, well, is that it's a fundamental philosophy, which means that I trust in Einstein, so we try to perturb something that in principle works very well. So the idea is, well, try to improve the Einstein theory, not by the introduction of a total linear theory. You just try to use the general relativity and perform certain modifications to try to fill certain weaknesses that the theory have. In this case, I encode this modification in this epsilon, which means to be theory with no metricity, f of invariance, several theories with modification based on astrophysics and phenomenology, etc., etc., etc. In general, you can also consider this like Einstein gravity plus corrections. There is Einstein gravity and beyond Einstein gravity. And you can also encode these modifications in the right-hand part of the effective Einstein equation, like an effective energy momentum test. So that is, that is in principle okay. You can also do this. You can also use this idea to investigate different kind of exotic matter, for instance. Okay. So the idea is try to investigate corrections to the standard Einstein gravity. In this case, just in 4 dimensions. So let me focus on certain observational motivations. And we know very well that since 10 years ago, Einstein gravity, in particular, the gravitational wave astronomy, the new gravitational wave astronomy, becomes very important and play a prominent role because now we can ensure that you can collect real evidence and confirm that black holes are real objects. Because, for instance, we have the direct detection of gravitational wave in light of these black hole mergers, and also because we have the first image of supermassive black hole, and in general suggests us that all this evidence confirm that we have a real object or real object which is a black hole. Okay, so the idea is well, given that you have data which confirm that black holes are realistic objects, the idea is try to extract as much as information as we can, and it's in this case this observational evidence motivate us to study different kind of different properties of these black holes. Okay. Originally, when the idea of black hole was introduced, usually we start considering an isolated black hole, but when the idea becomes more realistic, you have to accept that the black hole is not isolated. The black hole interacts with the environment, so you have to consider first some accretion disk. You have to consider some disk. After that, you have to consider that some interchange of matter, not interchange, but some matter fall into the black hole due to this accretion disk, and etc. So in general, when you consider a more realistic scenario, you can obtain or you can generate certain spectrum, which in this case is basically a figure in which you can describe how this black hole lose certain energy. Okay? In the most simplest scenario, when the black hole is isolated, if you prepare a figure and you show how was the energy. Okay, in an ideal system, the black hole don't radiate, but in practice, the black hole lose energy. And if you prepare a figure, you can see how this curve decrease in time. So this figure basically say you that you are losing certain energy. You can extract certain properties like the mass of the black hole, the angular momentum, depending of the background that you are studying, depending on this kind of perturbation or the response to certain kind of perturbation, or how this black hole lose energy, you can extract certain properties. Okay, so in general, when a black hole is perturbed, the response of the system is certain fluctuation, which means that this fluctuation is how the system reduces the energy. And this energy is basically how this energy is lost. It's basically the so-called gravitational wave. Okay, you can prepare a finger. This is basically the result of some collision in general in the best scenario of two supermassive black holes. They mix, and they produce certain wave. And you will principally see how this wave lose energy. Okay, is the idea. So in general, that is just pictorial representation of this work. You have three well-defined phases, the spiral phase, the negative phase, and the rhythm phase. And it's more or less a realistic spectrum. Here you can investigate how this spectrum evolved. And in practice, we are focused on the last part of the spectrum, the rhythm phase, because for the simplest scenario in first order perturbation theory, you can just extract information for the fundamental mode, or in other words, the first wave. Okay, so in principle, ignoring the details, you focus on this sector. From this frequency, you can, in principle, extract information of the black hole. Okay, the mass, or the angular momentum, etc. So let us focus on these frequencies. Okay, in general, these frequencies are standard numbers. Okay, but the important here is that such frequencies are usually called like quasi-normal modes. They are basically modes, and the prefix quasi is because you lose energy. In standard physics, when you investigate a certain problem in vibrational wave, you have a standard modes when the energy is constant. When you have a certain dissipation, you have quasi-normal modes, which are characterized by a negative imaginary value. Okay. So in this point, the quasi-normal are characterized by certain frequencies with a no vanishing imaginary parts. Okay? And in general, you have this definition. Okay? And the important point here is that according to this definition, depending on the sign of the imaginary part of these frequencies, you can falsify if this background is stable or unstable against certain type of perturbations. Okay, so in general, the idea is that using several methods, you can obtain different value for omega. You can plot this, and you investigate how evolve the real and the imaginary part. And depending on the imaginary part is positive or negative, you can conclude that the black hole is stable against certain type of perturbation. Okay, that is the main idea. Okay, also another important part is that the quasi-normal modes in general depend on the detail of the geometry. Okay, and that is not relevant the initial conditions. Okay, that is quite important because in general this the initial conditions are also missing in this kind of problem. So you can control very well the geometry. I mean, because you interpret the model, you can describe properly the physics, but you don't know very well the initial conditions. So that is an advantage for trying to extract the information. You control very well at least this part. Okay? And also you have to relevant identification here based on the physics of the vibration wave. The real part of the quasi-normal frequencies is directly related with the period of the oscillation. Okay, and the imaginary part is related with the decay of the fluctuation. And in particular, that is this part describes certain scale time, okay, which is the fluctuation decay. Okay, so we have several motivations in addition to the confirmation of the existence of the black holes. We have several other motivations to investigate quasi-normal closely related properties like the gravity factors and the absorption cross-section. You can find three very good reasons. One of the more important is trying to estimate the black hole parameters. Okay, in particular, when you investigate or when you compute the gravitational perturbations, which are the more relevant perturbations because you can contrast the observational data, can infer the parameter of the model. Okay? That is one of the more relevant motivation in a bit. Another motivation relevant is the well-known correspondence between the gravity factor quasi-normal modes and black hole shadows. That is, that's not so new. I mean, 3 or 5 years ago, the idea started to evolve, but now the people is convinced that this relation is very important, at least to make progress in gravitational wave astronomy. You have another motivation is try to quantize the black hole area. At least this was one motivation in the case of the trash black hole. I think you can in this last point there are some parameters. This is define some parameter to quantize the black hole area. So and that is in relation with the quasi-normal frequency. Okay. Okay, let me move to the concrete problem. The idea is okay, study certain type of black holes. Which kind of black holes? First, let us try to study some black holes with some astrophysical motivation. One motivation could be try to include the dark matter problem in this situation. For instance, we know very well that if you compute the velocity rotation curves, these curves are not in agreement with the spec. Because what's the reason? Well, basically because dark matter is not well accounted. Okay. Some years ago, around 10 years ago, some guys noticed that the tangential velocity of rotation of this curve can be related directly with one of the components of the metric energy momentum of the metric of the line element. And with this, with certain relation between the energy momentum tensor, with some concrete relation, you can also generate the density profile which is appropriate to obtain the velocity curve, which is expected. I mean, we don't have any, we don't found certain velocity rotation according to the spec. Okay, so the idea is okay. Let us try to introduce this effect, and how we can do that? Well, the idea is to introduce by hand certain matter content. In this case, using taking advantage in some relationship between the energy momentum tensor and the density and radial pressure have this relation in 4-dimensional space-time, and the tangential pressure are the same. And we have several different pressure factors. I mean, the different 1 divided by 2 between the radial pressure and the tangential pressure. Okay. And with this in mind, in principle, you can correct the metric potential, and with this, you can obtain some velocity curve with the suitable behavior. That is just the motivation of this equation. Okay? With this, you can, in principle, describe properly dark matter. Why? Because when you compute the velocity curve, you have certain form of this curve. You perform these steps, you obtain the same curve in the appropriate way. So that's the reason why you say that with this you can include consistently dark matter. Okay, that's the first part. The second part is okay, try to study this in a regular black hole. Why regular black hole are relevant? Because we know that, or at least we believe that this when black hole is not regular, we we interpret this like a Einstein gravity phase, in the sense that you have some fundamental similarity. So let us try to focus on backgrounds in which you don't have that problem. And we will focus on one of the simplest case, which is the Barney black hole, just like a toy model. This originally the author introduced this without any justification, but after that we found that other authors found that we can with certain nonlinear electrodynamics you can find this solution. So with these two ingredients, the previous one about dark matter and taking this into account this source, the idea is try to solve the corresponding effective lines of the equations to obtain a regular black hole and a solution where the dark matter is included. That is the idea. Okay. So that is the meaning of the parameter that we used in the previous slide. Okay. And the idea is basically solve this without any additional constraints, because that is very well known. The constraint regarding the dark matter was previously explained. Well, the motivation of that is, firstly, the motivation of this term is purely astrophysics, and also you can find certain papers, for instance, in classical and quantum gravity, where ensure that with certain relation between the radial and tangential any momentum components, you can find some well-defined geometry. Okay, so we can solve this using the spherical symmetric line element, the standard answer. And you basically find this solution, okay, which is basically the Barnum black hole plus this correction. And this logarithmic correction plays a critical role here. Okay? This is big. I mean, with this in the numerator, and this in the numerator. Okay? Because with this, the velocity of rotation acquired the suitable form. So with this in mind, the idea is to study how this well-motivated background respond against certain type of perturbation. So in general, you have a scalar, vectorial, and tensor perturbation, and also direct perturbations. In this case, let us focus on scalar and direct perturbation because that was the previous work. And in other papers, some other guys complete the massless perturbation. I don't know if the gravitational perturbation were computed, but the idea is just focus on the previous paper. Okay? So let me mention in summary how to face this. Okay, irrespectively of the kind of perturbation, the idea is solve certain the equation for the scalar, Dirac, or vectorial tensor perturbation. In this case, I will focus on massless scalar perturbation that was previously computed, but that's just to keep all the procedure, all the idea in mind. Okay, so in 4 dimensions for a massless scalar field, you have to solve the corresponding Taylor equation. Okay, in 4 dimension space-time, you have the standard. So you have to use the separation of variables, and conveniently you first collect the first term where the quasi-normal mode is encoded. You have the second term which encodes just the radial part, and you have a third term or third factor which encodes all the angular contribution. Okay, that's the value of the angular part. Okay, so in general, if you modify the dimension, basically you just modify this part and the index of this term. Okay. So there's no complex, it's easy to generalize. So the idea is, with this in mind, you introduce this in the Taylor equation, and you split this in the radial and the angular part, identify the corresponding values, introduce this in the radial equation, and with this, you can, and taking into account the identification of the metric potential, you can obtain some effective equation, which is called the naming of the perturbation Serine equation, or or well, depending on the case, this equation takes certain concrete numbers, but in certain concrete names. But in general, there is a Schrödinger-like equation in the sense that you have a second-order differential equation with certain effective potential. Okay? So when you manipulate a little bit the equation and using this redefinition just to compactify the domain, you obtain this equation. Okay. Well, this equation, irrespectively of of how complex could be the problem, the idea is mostly the same. That is a eigenvalue equation. So you have to solve this to obtain omega, and basically that's all. So the method depends on the complexity of the effective potential, but it's just a technical problem. The underlying idea is the same. For massless scalar perturbations, this is the effective potential. Okay, as you notice, you have a general form. Of course, assuming the Schwarzschild answer, which is that GTT is the inverse of GRR, okay, but that is standard in 90 or 99% of the works. And that is the general potential for massless scalar field. Okay? So given the last function, you can compute the corresponding effective potential for scalars. Okay? And the problem, because that is a second order equation, you have to supplement this with certain boundary condition in this case. In terms of this special coordinate, which is called the tortoise coordinate, with these two boundary conditions and with this effective potential, you in principle can use any method that you prefer if the potential is well defined, obtain the value of omega. Okay? And importantly, we have to remember that phi, I mean, it's like exponential of this of the quasi-normal frequency, and when you have a negative imaginary part, that implies that you have a stable mode. That is the take-home message of this part. Okay. What if we include massive particles? Well, the equation is mostly the same in this case. So you just have to include this, and the procedure is basically the same. Okay. You just correct the potential by the injection of this massive term. Okay? So the procedure is exactly this. So, okay, previous to move to the results, let me complete the scenario by considering what happened when you consider massless, when you consider particle with speed. In this case, with this y divided by 2, 1 divided by 2 particles. Okay? So, in the case of fermions, you just have to solve the one first order differential equations, but for two different fields. Okay, so you have to solve this equation, the linear equation. So you have to take into account the relation between the gamma matrix, the linear matrix in pure space-time. You have to remember this, how the gamma matrix looks in flat space-time. These are the algebra, okay? And these are extra relations. And that is very well known. That's the reason why I try to summarize this in the results. Okay? So the idea is mostly, in summary, for massless direct fields, you have to construct basically these products. Okay, that derivative and this G. Okay. Okay, with this, basically, now B act like this, you have gamma, and you know how the algebra works. So this is in principle. Okay. Now you have two fields, okay? For fermions, okay, you have two fields. You have two different functions, and the idea is, okay, given that you have two different functions, you will have to solve two differential first order equations. That is the case. Okay, That is, this choice is because you are in four-dimensional spacetime, because you are considering spherical symmetric spacetime, and because you are considering the answer, the actual answer. Okay, if not, usually appears some combination between GRR and GPT. Okay, when you replace this in the previous equation, you have a first order differential equation for the tortoise coordinates. And as occurred in standard electromagnetism, for this kind of coupled differential equation, you derive and mix this equation to obtain some second order differential equation with the mixed term, with this term, sorry. Okay. Second. Okay. Oh. Okay. So we have to introduce certain redefinitions in terms of the lapse function. Okay. You introduce this W function to rewrite the equation more conveniently. Okay. And you can introduce this extra, it's like the angular number, okay? Well, the angular momentum here. And you basically introduce this parameter, which is related with this original, and this with the original L of the scalar case, okay? So in summary, depending of this parameter, you will have this different modification depending on the perturbation, okay? For C1, 2, 3, etc. You can modify the spectrum and investigate how the perturbations, how the kind of perturbation, or how when we vary this number, the perturbation is modified. Okay. Okay. You have two coupled differential equations for f and g that combine this, and you obtain this two equations. Okay. And at this point, the situation is mostly the same in the scalar case, because you have exactly the same differential equation. All the problem is depending on the potential. Let us try to obtain the solution. In general, you can try to do this analytically, but in practice that is mostly impossible, and you have to use semi-analytical approach, or in general numerical approach. Okay, that's more or less the idea. But up to now, at this point, the treatment is the same. Notice that you have two different potentials because the sign is different. Okay, in general, the potential is not the same. In general, when you have a fermion, the problem, this problem broken is a spectrality, so you have to compute the problem for the A plus and B minus case. Okay. In general relativity, simple general relativity, in principle that works, but in any theory, another theory with additional ingredients, you don't have any guarantee that the potential are the same. Okay. Okay. Let me focus on one of the more simplest methods to compute the Cosmology frequency, which is the WKB method, which is a semi-analytical approach to obtain these frequencies. We basically learn this in some standard course in quantum mechanics. And the idea is, well, based on certain expansion, okay, you can modify this perturbatively, increasing the order, trying to modify or trying to increase the precision. But that is, you can do this, but that's not the case. I mean, you can improve the method, but improving the method don't guarantee that you improve the results. So this is the general expression, irrespectively of the order of the method. You can always have the same expression, and when you modify the order, when you increase or decrease the order, you have to modify this lambda and this omega. Okay? So depending on the order, lambda and omega vary. You can find this in the original paper, and that is not necessary to do nothing because that is a general expression that works very good. And you have the meaning of the parameter which appears in the expression, but in general, the take-home message is okay. You just need the You just need the effective potential evaluated in the maximum, in the peak of the potential, okay, and some derivative of this potential. And with this, and knowing the order of the approximation, you can obtain the corresponding frequencies. And when you vary consistently, you can collect all these frequencies and generate some plot, and that will complete the spectrum. Okay, that's the idea. So when you can apply this method, well, you can use this when the effective potential have this convenient form of certain barrier potential, like in quantum mechanics. That is quite common, but it's not the general scenario. You have certain case in which when you compute the effective potential, the barrier can have certain plateau, and in this case, you cannot use this method. Okay, that's some weakness of the method, but in general, when the effective potential have this form, it's in many of the simplest black holes and the more popular, more investigated black holes, the method can be used. Okay, okay. And you have plot this in this in the using the turquoise coordinate for simplicity, because if not, the spectrum looks. I mean, the spectrum of the effective potential looks different. It's not symmetrical. Okay. So just to supplement or to confirm that the numerical results were well computed, we use some other quite simple method to compute the quasi-normal frequency, which is the Borch-Teller method. That again, I will ignore all the details because it's, the computation and the derivation were made many years ago. But you can find some close expression for the quasi-normal frequency. And the idea is, okay, how you can find this expression? Well, you replace the original potential by some other potential, some analytic potential, and with this in mind, you can reconstruct the differential equation. And in terms of the derivative of the potential, okay, you can find the quasi-normal frequency. So basically, you have this. The idea is, based on the original equation, you replace the real effective potential by some other approximate potential, something like some hyperbolic cosine or something like that. And you modify a little bit you work a little bit the expression, and you can find this the quasi-normal frequency. Okay. The important point is, okay, that is, notice that you have the real and imaginary part, and just the imaginary part depend on n, which is one of the weaknesses of this method. Okay, that's not much important when you consider no values of. Okay, this is the standard form of the effective potential for the scalar. In this case, for massive scalar perturbations, that is because we are plotting in standard radial coordinate, not the tortoise coordinate. If not, you can find the potential like a symmetric barrier. And these are the corresponding quasi-normal spectrum. The quasi-normal spectrum means when you plot the real and imaginary part in the same plot, but I have certain parameters. For instance, in this case, we fix the mass of the perturbation, the mass of the black hole, give the parameter of the nonlinear electrodynamics. We take n equal to 0, and we vary alpha, which is the parameter we both the Darmater correction. Okay, so for different values of alpha, you compute and you obtain 1 point, 2 point, 3 point, divide from 0.1 to 0.9. 9 points for per core, okay? For L1, 1, 2, 3, 4. Okay? And you basically have the spectrum. Okay? That's just 50% of spectrum because you can plot the left-hand side of the figure. That is using the Borch-Teller method. And you obtain mostly the same using the WKB method. Okay? I put this in a different figure because it's not easy to see the difference if you overlap the two. Now we show how the real and the imaginary part evolve with this parameter, with alpha. Okay, we observe that, for instance, the real part of the cosmological frequency decrease. Okay, decrease, but increase when air increase. For instance, notice the color here. The purple is 1 and red is 2. Same here and same. So you increase L and the real part of the cosmological frequency increase for certain alpha, or decrease in general when alpha increase up to 5. Okay. Okay, you can do the same for the imaginary part. In this case, in the post-Taylor method, using the post-Taylor method. And now let me show you some of the comments that the referee suggests for this paper. We show in a figure the relative error of the two methods. Okay, so we observe that, for instance, for L equal 1 and when you consider L equal 2, 3, and 4, the error between the two methods decrease significantly when you increase the as it should be. Okay, that is the real part. Okay, that is the imaginary. Okay, so when you increase L, the difference between the two methods is around less than 1%, which is a good agreement. Okay? So for the quasi-normal modes, but for direct particles, you repeat the procedure and compute the corresponding direct potential. Looks as always in the same that you have maximum and that decrease for different values of the parameter. And you obtain again the corresponding quasi-normal spectrum. Okay? So as you notice, the imaginary part is always negative for scalar and for direct perturbation, which means that the black hole is stable against this kind of perturbation, at least for the parameter that we are using. Okay. The same occur for well, that's this for check. Okay, post-Taylor and WK. And finally, that was the part regarding the quasi-normal mode, and let me move this to the part regarding the absorption cross-section, which is a topic related to the corresponding quasi-normal. Okay. Okay. The gravity factor is given by this parameter. This is basically physics of transmission and reflection of wave, most in events. Perhaps it's not the better presentation, but the main idea is just to investigate how the propagation of a wave evolves in terms of the coefficient of transmission and reflection, basically. Okay? So the gravity factor of certain black hole is given by this term. Okay, this usually the transmission term, which is the probability of the wave tunneling through the potential created for the field in consideration. I mean, in summary, it's when you compute. Okay, this expression is clear. Okay, when you consider the transmission plus reflection is equal to 1, so you are interested in consider this term, the reflection. The reflection here is given first by this expression in general, irrespectively of the approximation, that is the general expression. And all the physics or all the approximation should appear in this parameter. The parameter B encodes the order of the approximation. In this case, you should WKB approximation. These two expressions are totally general, and the idea is for certain approximation, B takes some concrete form. Okay? So in this case, B acquired this simple form. This is because we are using the WKB approximation up to third order. Okay? We can also, in general, the sixth order is more convenient in general, usually, but third order, when you consider direct perturbation, is slightly more convenient just because that's just because a numerical problem, numerical efficiency. Okay, it's not a problem of the method. It's just because it's time consuming when you try to run the routines. Okay, so in general, the idea is okay. For the order, you have this expression, and the idea is compute the absorption cross section, which is this expression. Okay, and you have to first this expression is basically the sum of all the cross section for different L. Okay, and this is related with the transmission coefficient. So with this expression, having computed the transmission coefficient, with this factor, you compute sigma L, and which is you sum over all L, you obtain the corresponding absorption cross section. Okay, and what is the relevance of this? Well, let me show you in a figure, for instance. In general, it should be, I mean, this curve should increase at certain point, obtain certain plateau. But in this case, when you are considering massive particles, and with the inclusion of this extra contribution of the dark matter, you observe how the last part of the figure is strongly modified. Okay, the same occur when you the previous is when you vary alpha, and the last one is when you vary mu. Okay, you still can observe certain modification on the last part of the curve, and that is because the inclusion of alpha and mu affects significantly how the black hole respond in this set. I put all the main idea in the conclusion, but the idea is okay. The inclusion of some mass and the inclusion of massive dark matter effects modify significantly, at least in this part, more evident the profile that with respect to the quasi-normal modes, the absorption cross section. And in general, you have the take-home message. The first one is regarding the quasi-normal modes. Okay, that in general you obtain stable solutions for direct and massive particles. And here you have the two conclusions based on the previous figures. Okay, so well, you can check this because I'm on time right now. And that's all. Okay.
Thank you, Angel, for your talk. Questions or comments?
Yeah. For your first slides, second one.
Very well.
Sorry. Yeah. The ones that had Q alpha mu plus G. Here's this one.
Okay.
So the second term on the right hand side describe what?
This one? Sorry.
Yes, this one.
Okay.
This describe what?
Okay. The idea here is symbolically describe modification of the Einstein equation. I mean, in general, you cannot, or according to my experience, you cannot add part of this sector. You can also include part of this sector. That is just a representation in the sense that the first term is connected to general relativity, and the second term shouldn't count any deviation. But I'm just modifying this part. Okay, this is just symbolic in the sense that all the equation is consistent, because when you introduce this, of course, you are not considering just general relativity. You have to extra ingredients.
So extra degree means any modified states?
Yes, that's just
Like of R.
yes.
So
It's
in
symbolic.
that case, the equation is not a balanced one.
Uh,
There is a difference between the units. For example, G mu, the Einstein tensor, it depends on Richter scalar, which behave like part of.
No, but in the okay. To be more precise, if you want to be consistent with the units, the more convenient scenario is try to introduce prefactor in the action, which account this potential difference of the unit. I mean, instead of introducing variance, you can introduce alpha plus the time the invariant in such a way that the product remains with the adequate dimensions. It's the more convenient way to avoid problems with the dimensions. I think, I mean, instead of include just invariant, just put by hand some numerical prefactor, some scalar to adjust the dimensions.
That's a practical case. This must be taken into account. In the calculations, this must be taken into account.
In this case,
Yeah, generally, you must adjust the units to be able to show the correct value.
well, I mean, in general, according to my experience, when people introduce this by hand, in general, introduce free parameters, and at certain point, they check and adjust the numerical prefactors. Usually, according in terms of kappa, H, E, G, etc.
Okay. So you take into account this case when you calculate some numerical.
Yes, usually. If you, I mean, in general, it's convenient, it's a cross-checking relevant. Because if not, you cannot make sure in which if you are accounting one part more than the other, you know? So because the numerical values are relevant when the numbers are so small.
Okay. So the other thing is a form of f of r that you start with. Yes, this one. So the last term, its contribution comes from the energy momentum tensor. The non-vanishing of the energy momentum tensor.
It's not, yes, it's not vanishing.
Yeah, this contribution of the last term comes from the energy momentum.
This term,
Yeah.
this term comes from the constraint of the of this part. Of this part. Because the logarithmic correction usually
Yeah, so the energy momentum tensor.
yes, exactly. For this part. I mean, the intermediate part is missing, but that is
Yeah. So if you are dealing with vacuum, you return to the Verdine black hole, which is the regular one.
Can you repeat this?
If you deal in vacuum case, so in that case, you will recover the regular black hole.
Exactly, yes.
Okay, any other question or comment? Maybe online? 5 seconds to say anything? No?
Okay.
Then let's thank Angel again. It's time for our second speaker. It's Nestor.
Do you think me to
Cambiamos de
do I destroy this? Okay.
Cambiamos de pie. Ahí está.
Vale, pues he conectado mi pasador de.
Ya me lo dirás.
Deja de compartir.
Anteriormente, ahora sí que. Sí.
The case because he has finished his master and he is looking for an opportunity to study teaching. Oh, yes, you are studying Madrid in the University of Madrid. And he's here to tell us about a very interesting work he has done in his master. So please, whenever you are ready. Thanks for Yeah.
approaching scale. But you can line. You can see it there. Now this is it.
Now, I guess that everybody can hear us.
This one.
Okay, now I guess that everybody can hear us.
That's
For the audio was not working. So that's
from
is coming from not sharing.
Not sure why I'm not.
Coming from the so next is coming from the university. And he fully will be able to share. Okay, now
I think now.
if it works here, it works here. Okay, very well.
Go ahead.
So go ahead.
Sorry. Yeah. I will try to go fast. I think my presentation is not as long as the previous one, so I think we can save some time. Okay. So everybody, since I'm the rookie,
I don't know
as much as you do, I will be skipping. Not skipping, but I always going fast slides because I assume you will know more than me in this topic. Okay, so but the topic I'm going to talk about is a non-finished article that we are trying to write with Alvaro and Gonzalo about orbits in static and spherical symmetric stellar solutions in the Stravinsky model. So we're just doing FFR gravity, and we're interested in what orbits, what happens with the phenomenology of the orbits outside the space-times. Okay, so first of all, as I was saying, I'll go fast. FR theories, we all know FR theories have a basic Einstein-Hilbert-Lagrangian, or action in this case, and you just add this little term f of r, which okay, it is kind of really, but I think I will do it with okay. If this f of r term, and varying with respect to the metric, we can also do it with respect to some connection or whatever, but we assume the Levi-Civita connection. So we metric formalism. We get these field equations. In our case, we will be working with the Stravinsky model, which is the most basic one, polynomial that we can get. Now, just because of the same reasons that the previous lecture told us, we're going to use compact objects to study these because they present the most extreme conditions, and so we can get the largest results to test our theory. So now we're going to use neutron stars. So we're going to assume that we have a spherically symmetric metric. So we only have A and B as the coefficients, and then radial stuff. Also, we will assume that the neutron star is, of course, a perfect fluid with an equation of state. In our case, in this paper that we're writing, we're using 3 equations of state: soft, mid, and stiff from the bibliography, and that will be it for now. Yes. So now, from this, using all this along with the field equations, you can get a system of ODEs that you have to solve. But first, we have to pay some attention, and I think that's something that some people don't do in some articles before. They just assume some external spacetime. We have to pay attention to the junction conditions at the stellar surface. So, of course, we have some initial conditions and some asymptotic conditions I will say later. But the most important ones in this case are the junction conditions at the stellar surface. So in GR, if you're working in GR, we have to impose the continuity of 2 things. First one is the induced metric, so just a projection of the metric on the stellar surface. And that imposes immediately via the equations that the first coefficient, A, has to be continuous along the star. Then we have to also impose the continuity of the extrinsic curvature, which is basically the projection of the derivative of the normal vector along the surface, how it curves, okay? And that imposes also how B and the first derivative of A has to be, they have to be continuous at the border of the star. Not only A, but also the derivative in this case. But now in FFR, we have some new things because some distributions appear when you do the equations and some of them cannot cancel. So you need some things also to be zero, some changes to be zero. In this case, we need to add the scalar curvature and its covariant derivative along the star surface to also be continuous, okay? Not in all FFR theories, in the ones we are interested in, like Starobinsky, we need to do this. Okay, the other main conditions that we need to ensure is for non-divergent central pressure. Again, you look at the system of ODEs, and you need some parameters to be 1, 0, R prime has to be 0, and if you have all that, you can have a central pressure that is a value that we can choose. Okay, that will be the free value that we will be choosing in order to create new stars and integrate new stars from the inside out. Now, another important thing, even if we are in FFR theory, we have to ensure asymptotic flatness. So we need the coefficients to be tending to 1. We need to tend to Minkowski. And so we will just choose a value of AC, a value of the central value of A. Doing something that we call a shooting method, we just try to fix it, extrapolating to the infinity to get that. And it's just a numerical process. We're doing everything is numerical in this paper, of course, mainly because the equations of state that we're using are numerical. So there's no other way. Now, to avoid this discontinuities in the energy momentum tensor, we need just, to have a pressure and energy density of 0 at the star surface. And that's actually not something that we pose. It's the thing that we use to determine the star radius when we are integrating the star from the inside out. You start integrating the system radially, and the moment you get to a pressure or an energy density of 0, then that's what you determine, okay, this is the radius of my star. Then I can continue outwards, applying the conditions, the junction conditions that I was saying before. And now, because of computationally different things, we have to use as a suitable approximation from GR that at least the initial value of the scalar curvature is going to be the same as in GR, okay? There's some papers that prove more or less that this is a suitable approximation, okay? So what are the results that we get from the integration of these equations? There are some results inside. We're only interested in the results outside the star. So the coefficients A and B, now the letters are really small, but A and B, so the time coefficient and radial coefficient of the metric, we see that the dotted line, which is the GR line, is more or less the same as in FFR. For B, you can see a little oscillation, and that's actually the same thing that happens with A, but you cannot see it because it's really small. But the coefficients work as they should. They are almost as in GR. They tend to 1 from below or from above, but that's it. And the most important part here is the scalar curvature. This is the nice new thing. As you can see inside the star, this is the radius of the star. Inside the star, things happen. We don't really mind right now. But outside the star, of course, in GR, what you get is that the scalar curvature, because there's no matter there, is just 0. So the scalar curvature that you should get is 0. In this case, it's not. You get an oscillatory, let's say, function around 0, of course, and that will tend to 0, but it's oscillatory, and that will create some kind of gravitational sphere. If you understand this in a scalar field, you have the scalar field, vision of this FFR theory. You would have some scalar field with some associated mass that will be adding it. You should be adding that mass to the mass of the star. So the inside mass of the star and the gravitational mass of the star far away from it are different. Okay, so that will be interesting. Now, the thing we're interested in now that we have the outside proper junction condition checked space-time, we have to check what happens with the stable circular orbits. That's the first thing we wanted to try to see. So we start with the Lagrangian equations, from the metric, and we're going to apply the Euler Lagrange equations. So we get the usual equations that we all know, where K is now the specific energy of the particle that we want to orbit, and H would be the specific angular momentum. Okay, so for now, this is just normal. We're just leaving A and B without entering the GR values, because of course this is numerical and it's different from the GR values. applying now the conservation, well, we can get a conservation of energy law if we just assume the particle is massive in this case and put the Lagrangian to 1. And what we get is the usual energy conservation equation. We have an effective potential, we have a kinetic energy. Interesting kinetic, because usually AB many spacetimes will be 1. In this case, AB will be an oscillatory function also. So this term is also quite weird, okay? But the effective potential will be this, and this will amount to the energy, so that if K is 1, then we get that the effective, like the potential and the kinetic energy are equal, so we have a just bounded orbit, okay? Now, what can we do from this? We need to impose, if we want the circular orbits, we can impose circularity. We can impose it by doing r dot, of course, meaning with respect to the proper time parameter. And also we can assume that the effective potential with a minimum in the effective potential in R0. R0 will be what we would call, let's say, a turning point. Turning point meaning it's a point in which all the movement is non-radial, it's all angular movement, okay? So that's what we will have. And now from these two conditions, what we can get is expressions both for h and k in terms of the radius that we want. So what does this mean? It means that we can choose a radius, and from this radius, if we want to have an orbit that has at least instantaneously a totally angular movement, we can tell how h and k, which values h and k go down. So I check 600 kilometers away from the stellar surface, and I get, okay, then h has to be this, and k has to be this in order for you to have, if you can, a circular orbit. Now we go with it if you can, because sometimes, and that's one of the funny parts, you cannot. So we have to check some conditions of existence. Okay. First condition, basic condition, k squared and h squared have to be greater than 0. Of course, if not, you have an imaginary angular momentum or imaginary specific energy. That doesn't make any sense. So this is the physicality conditions. Of course, if we want to have an orbit that is not, well, a bounded orbit, we need it to be bounded. So as I said before, if k squared were to go above 1, then we would have that the energy being kinetic minus potential would be greater than 1, so it wouldn't be bound. And the last one will be just the stability of the orbit. If we don't get stability, of course, we have instantaneous angular movement, but little perturbation will throw the particle away. Okay. From these three conditions, expanding the effective potential as I showed before, we can get three radial functions that I have chosen like this to be always things that we want to be greater than 0. It's just I move everything to the left, that's just it. But we have these three condition functions. And if this condition function follows, then we have a physical orbit, a bound orbit, a stability, or stable orbit. Okay. And what happens with these, since all of these are oscillatory functions, because A prime is oscillatory, A second prime, all this is made from oscillatory functions, we will get something that I decided to call orbit behavior rings. I will explain. Okay, so this is just a piece of the distance 860 to 870 from the star in kilometers in this case. Okay, so as you can see, these functions are greater or less than 0 periodically. So for example, C1, the existence condition function, here is greater than 1, less than 1, greater than 1, less than 1, and it goes periodically. Then we have another condition, the boundedness condition, and it doesn't coincide with the first one. And then we have the stability condition. All of them are periodically oscillating, but the combination of the three conditions leads to different possibilities. For example, whenever we don't have the existence condition, the physical condition, we just cannot have any orbit. So that means if we try to feed our equations this radius, I want an orbit at this radius that has a turning point, so a perfectly just angular movement at this specific point. Well, the equations will drop bullshit, okay? So they won't work. Will be imaginary or whatever. if you have existence and boundedness, but you don't have stability, then you have precessing orbits. So there are moments in the precessing orbits instantaneously that you get a perfectly angular movement, and then the particle falls again, and it just does this classic flower pattern of ellipses with a lot of precession. A lot because we're doing neutron stars and we're really close to them, so the precession is really, really big. If we don't have the boundedness, but we do have the existence, we have the unbound orbit, of course. It doesn't even matter if it's stable or not, because it's already unbound. And in that case, we will get just, a hyperbolus basically. And lastly, the things we're more interested in is the circular orbit, but just these little regions where all the three conditions meet are the radii, at which you can actually have circular orbits in this space, which is a really weird thing to say, because usually in GR, of course, when you're farther away than the ISCO, the innermost stable circular orbit, you can always have circular orbits around a neutron star. In this case, you cannot technically. We can also check numerically that the eccentricity of these orbits is in accordance to what we get. And of course, when we get in the radius of circular orbits, the eccentricities that we get are 0, circle. Then in the unbound orbit, it suddenly goes above 1, and we have this smoothly varying thing. At the moment it drops to 1, we enter into the precessing orbit area, and then into the no orbit again, where we can just not plot the orbits because there are no orbits there. Okay. This is an example, for example, of some orbits that I plotted. Some are, they are, I think, in this actual range. So they're like a kilometer apart. But when you force the turning point or the angular movement point at that specific radii, these totally different things appear. So it needs, if you want to have this point here, then you will have an centralized eccentricity more than 1, less than 1, perfectly circular. And they actually are really close to each other. But if you want to force this, they turn out completely different. Okay. Okay, but now we will go back to the circular thing. Okay, that we showed that there can be some other things that happen outside, but the most important thing right now are the stable circular orbits. So if we just focus on where the circular orbits can exist, we get this existence rings. And then now there's some phenomenology that can happen. Different phenomenology. For example, this is a plot of the 3 condition functions. As you can see, C2 and C1, stay always above 0, so they are always met. They actually, we have some big lines and then some oscillatory lines around. For these 2 functions, there's also an oscillatory version of it, but again, the oscillations are so minimal that you cannot see them. Okay, but they are basically above 0, for the whole period, because the oscillations are also so small. But for the third one, something interesting happens. We can see, yes, because for GR, this thick curve would be the GR counterpart of this. There's a point around here that would be the ISCO, the innermost stable circular orbit, because now all the 3 functions are met, all the 3 conditions are met, so we can have orbits, circular orbits. And from then on, you can always have orbits because all 3 functions are positive. But in this case, since we have a really, really big oscillation, you get some periods in which this is not the case, and you cannot have stable orbits, circular orbits. Okay? So this is and now also one of the interesting parts is that this, as you can see, this peak goes up before. So the ISCO, this theory, will lay before closer to the star than the GR predicts. Okay? Because this crosses 0 before we expected it, let's say. Something interesting happens when you move the parameters along. Of course, on these graphics, I'm changing both the central pressure of the star and also the parameter A that mediates how much Star-Rubinski model are we applying. So the AR squared, how big A is in absolute value, because it's negative. And if you treat the values, sometimes you can get this, and all the oscillations in some part near the star all the oscillations lay above the zero line. So we get this that I call a principal ring, this principal really big ring in which every value is accepted, and you can get circular stable orbits all around here. Okay, and then from that point on, you just get rings again around in this case, around 1 kilometer thick. Some of the things that can happen, interesting, are the behavior of the ISCO. This, in general, is similar to GR. In some cases, you can get that this, in this case, is the radius of the star, and it's also the ISCO. So meaning the functions all start being positive. They don't have to come from a negative phase. So in that case, we have orbits even as close as we want, arbitrarily close to the star surface. And then we have a principal ring and it stops. We also have some situations in which you have orbits as close as you want, but you don't have a principal ring. There are all sorts of combinations. And now we started basically checking the phenomenology of all these new weird stuff. One of them that I wanted to check was the width of the principal ring, which was how could we know how wide this principal ring will be. And if we plot, depending on the value of A, so how strong our effect of the Stravinsky theory is, or how close we are to GR, if you want to see it that way. And then the mass of the star, which is completely related to the central pressure of the star also. We have this gradient in which we can see that for lighter values, we have a principal ring that is wider and then smaller. And some black areas in which you can see, well, there's just no principal ring at all. For example, in the medium, these are 3 graphs from the 3 equations of state that we have used. They behave, as you can see, pretty different. But for some of them, for example, there's some even some level curves that you can actually get, some smooth level curves. Remember, this is all numerical, and it's computationally difficult, so it takes time. But you actually get some level curves. And what we see in general is that the bigger the value of A is, so the further away you are from GR, you actually have smaller principal rings. And actually, when you're really close to GR, that's when you get the principal ring that's really big. We can imagine that in the limit, when you go to 0, so when you go to GR, the width of the principal ring becomes infinite, and then you have that everything is the principal ring, and according to what we all know, every orbit is accepted. Also, it changes with the pressure, or the mass. In this case, this is the mass, making it so that for bigger masses, the width of the principal ring, the biggest widths are in little, like smaller Stravinsky parameter values. So, and the other 2 things that we wanted to check for now was the distance to the ISCO, because we saw, as I said before, that the ISCO doesn't lay the same point as GR. So, for example, we have here that for, again, the masses and the value of A, you get that the distance to the ISCO to the stellar surface, so how far away we don't have any orbits at all, this first ring of nothing, no possible orbits, I mean, stable circular orbits. When the region is black here in these graphs, that's what it means. Well, what it means is that the distance to the ISCO is 0, so we have arbitrarily close orbits to the surface of the star, and then it goes far away. And again, the smaller the value of A is, and the bigger the mass, we get higher and higher values of the ISCO. Okay, so it gets far apart. This is for the 3 equations of state again. Forget about the points; it's just referring to some other plots in the article, and that's, as you can see, for the soft equation of state, you get a lot of points in which it coincides, but as you go stiffer to the stiff equation, there's almost every time you have at least some distance to the star when it's more compact. When you use that equation of state, that being stiff means I think it has to do with the pressure waves and how the matter compacts as you go outside the center of the star. And also, not only how far apart from the stellar surface we have it, but how far apart from its GR counterpart. It's an interesting thing to check. And actually, the graphs, as you can see, they look really similar, but inverted. And what we have is basically that When you have low masses, basically, and in this case, the value of A doesn't even matter that much. But when you get low masses, the difference between how far away the ISCO is in GR and F of R is the biggest one. And for bigger masses, up to 2 stellar masses, you then get almost no difference if the value is small enough. Sarbanes value is small enough for all equations of state. So for now, the conclusions for now, which is, as I said, this was gonna be bust because it's half a work and I'm the rookie again, so forgive me. In FFR theories, we have to apply some extra junction conditions, and this is something that from some papers that I have read, some people usually. I mean, it is a good approximation. If you're not going to use the value, you're not going to use the outside metric because you don't need it, then you're going to assume it's Minkowski, sorry, Schwarzschild, and that's it. But if we want to obtain physically relevant and proper space-times, we have to apply these junction conditions. The main difference that with GR when we do this is that there's an oscillation in all metric coefficients and also the scalar curvature, most importantly. Then these oscillating functions cause some existent rings of stable circular orbits because there's no continuity in the positivity of the conditions. And now in the phenomenology of all these rings, there's a principal ring that may appear that can be bigger and bigger as long as you go closer and closer to GR, which makes sense. And also the ISCO is always closer than its GR counterpart so that's also interesting. And it may coincide or not with the stellar surface. That's actually something that happens also in GR. So that's not a big difference. Whoops. And the thing that we saw in the middle, that if only some conditions are met, then we have also different behaviors that we can have in the middle. If we're not only thinking about the stable circular orbits, but which kinds of orbits we can have with a turning point at that radius, then we can have sometimes they have to be unbound, sometimes they can be bound, but they are not stable, blah, blah, blah. And for now, as I said, that will be all.
Thank you so much, Nestor. Comments? Questions? Or online, anybody wants to ask something? Well, I have some questions. What is, in your view, the physical explanation for these oscillations?
Okay, well, fun question, yeah.
And also, why in the interior solutions we don't see the oscillations?
Why in solutions we don't
Because
see
the interior is smooth, and then outside is when you start seeing the oscillations.
I will have to check that because I think for some values we can see oscillations inside. Yes. For some, but it's more difficult to see them, yeah. But inside we can get oscillations if you get to some extreme value. I don't know how extreme, but extreme quote unquote values of A or whatever. And now the physical explanation, well, yeah, as I said before, if you interpret this as a scalar tensor theory, you can transform these equations into having a scalar field that has an appropriate mass, that has a mass. It's a massive scalar field, and these oscillations would be just oscillations in the scalar field that I mean, how can I?
So maybe the scalar field, there's a scalar field that defines a second order equation.
Yeah.
Second order equation typically have
Oscillating
damping term, oscillatory term.
Also some diverging terms that we have to reject. That's also the reason why the A value of the Sarbanes theory has to be negative, because if not, you get divergent, and you cannot have asymptotically flat space-times. Of course, yeah. Actually, I started doing all my master's thesis work using this interpretation, like not looking at how the scalar field could play a part, but that's actually the way to see it physically, like to interpret it. So it would have been better to start like that, but I didn't.
so it's never too late.
That's it. Yeah, yeah, of course.
Okay, any other comments or question? If not, then let's try next one again. Coming from
I can hear you. It is muted here. Yeah, I think your computer is muted.
That's because my microphone was not connected. Okay, now
Yeah,
it's
yeah.
connected.
Now it's okay. Yes.
Okay, is the audio good? Is it reasonable quality?
Yes.
Yes.
Yeah, I can hear you
But we
perfectly.
cannot hear you because my audio is off. So is the audio good? Is it reasonable quality?
Yes. Yes.
Yes.
Yeah, I can hear you
But we
perfectly.
cannot hear you because my audio is off.
Wow.
Wow. So is the audio good? Is it reasonable quality? Okay, let me see. Okay, is it better now? Can you hear me?
Yeah. I can hear you.
Okay, very good. So, but let me see. Oh, wow, I can. Okay, is it no, better now? I know what happens. Can you hear me?
Yeah.
Okay, it was this thing. Because the YouTube channel was open also on my computer.
Okay.
Okay, so now I need Polycom Studio and the video Polycom Studio. Okay, now better. Okay, so Renan is currently a postdoc at the Federal University of Maranhão in São Luís, in Brazil. He did his PhD in Belém, the Federal University of Pará, in Brazil also. And he's going to tell us about anisotropies from Lorentz violation theories, from Lorentz violating theories. So, Renan, feel free to start.
Okay, thank you very much, Gonzalo, for the invitation. Hello, everybody. Today, I will talk about this work we completed this year. This work was made in collaboration with Leandro Lessa, another postdoc here in UFMA, and Manuel Bessia is my supervisor here. The idea of this work is very simple. We analyzed some Lorentz violating models and try to find the self-consistent solutions in these models. So let me give you a brief introduction. I don't know, are you seeing this bar here in the top of the presentation or not?
No, we don't see that.
Okay, perfect. Okay. Okay, so as you know, in 1915, Einstein proposed the general theory of relativity, the current gravity paradigm. I think I'm hearing myself now. I don't. Okay, no. Now it's okay. Okay, it's okay. Okay, so in 1915, Einstein proposed the general theory of relativity, the current gravity paradigm. This is the equations of GR. The left-hand side says about the gravity content, the geometry, and the right-hand side is the content of matter and energy in the space-time. This theory was tested in several regimes, including the low-frequency regime, and now in the last decades in the strong field regime. And it's important to say that GR is grounded in the symmetries of diffeomorphism and local Lorentz invariance, as you know. And since you are in this workshop, you know that GR is probably not the final gravity theory. We have a lot of reasons to believe that there's something beyond GR. In one hand, we have problems in understand the large structure of the universe. If we assume that GR is the correct description of gravity, to understand the universe structure, we have to include this unknown matter and energy content known as dark energy and dark matter. Also, GR predicts singularities. So even in the future of an observer, let's say in the future of a gravitational collapse, or in the past, in our past, in the beginning of the universe, there are theorems saying that singularities are unavoidable. A possible way to circumvent these issues is to include gravity in the description of, is to include quantum mechanics in the description of gravity. But as you know, this is a huge problem. But why this is a huge problem? Well, we have a lot of theoretical and philosophical reasons to believe that gravity and quantum mechanics must be together in a single framework, but we have a lack of observation and experimental guidance. So even we want to describe something and prove it, we don't have the experiments to confront with the theoretical predictions. And the reason behind it is that the typical scale at which quantum gravity should become relevant is the Planck scale, far beyond any experiments we can perform here in the Earth, or even any cataclysmic event in the universe. However, we also know that most of the quantum gravity frameworks or alternative theories of gravity have these low energy relic signatures, and in the low frequency, in the low energy regimes, one could find these observational signatures coming from this quantum gravity phenomenology. And one of these relic signatures is the violation of space-time symmetries. There are several quantum gravity frameworks and alternative theories of gravity that predict, let's say, in a very simple way, the violation of space-time symmetries. Here, we are not focusing in a specific model of gravity, of quantum gravity. Instead, we are looking for an effective theory perspective. So we are considering something like gravity plus tensorial fields, and these tensorial fields can acquire non-zero vacuum expectation value, and this induces a spontaneous breaking of the local Lorentz symmetry and diffeomorphism. Here we are considering the bubble B model. I think most of you know about it, and also an antisymmetric rank 2 tensor model, frequently known as Calvi-Ramon field. So this is the action we are considering. The Lagranges of these additional fields are given by these two terms here. And we are considering a very general approach where the bubble B and the Calvi-Ramon fields are coupled with the Ricci scalar Ricci tensor and the Riemann tensor. Okay, so the point is that how these tensorial fields, the bubble B and the Calvi-Ramon field can spontaneous break the Lorentz symmetry, basically via self-interaction potential. The form of the self-interaction potential is such that they can induce a non-zero vacuum expectation value to these two tensorial fields. And these non-zero vacuum expectation values basically create a preferred direction in the spacetime. So this is the general framework. We have this action, very complicated action, but as you know, we can take variations with respect to the fields and find the equation of motion to study whatever we want. So if one takes the variation with respect to the metric, one obtains the correspondent Einstein field equations. Here we are considering a potential cosmological constant term. So the left-hand side, again, contains the geometry of the gravity framework, and the right-hand side contains both the matter content and the Lorentz violating field content. It's important to point out that here we are not considering any coupling between the matter sector and the Lorentz violating field sector. It's possible to consider this kind of couplings, and as we'll see, these couplings can help in the constraints we will study here. But in this first work, we did not consider this type of couplings. Okay, so by varying the equations with respect to the matter fields, we obtain the standard equations for the matter fields, like the Maxwell's equations, Klein-Bauer equation, Dirac equation, and so on. And finally, by varying the action with respect to the Lorentz violating fields, we obtain the equations for the bubble B field, this first equation here, and the equation for the Calvi-Ramon field, the second equation. Okay, so the idea of this work is to study these two equations here. So basically, if we want to find a compact object for these Lorentz violating frameworks, we have to simultaneously solve these four equations. We are assuming here that there is a solution of the correspondent Einstein field equation. This solution is sourced by the matter content that satisfies the matter field equations. And together, we have to guarantee that the Lorentz violating field equations are satisfied. So this is the idea. The point is that when one is considering the Lorentz violating field equations at the VAV state, so at the non-zero vacuum expectation value state, the two Lorentz violating field equations become these expressions here. And if the field strength of the Lorentz violating field equations or the covariant divergency of this field strength is zero, then the left-hand side of these equations vanish. If this happens, then the Lorentz violating field equations, instead of dynamical equation, becomes more like a constraint, a geometrical constraint. So basically, imagine that we have either vanishing field strength configurations or covariant divergence free field strength configuration. The left-hand side of this equation, these equations will vanish, and what we obtain is a relation between the values of these non-zero VAVs related to some combinations of the Ricci, Riemann, and Ricci scalar tensors. So here we will consider these specific constraints for a spherically symmetric spacetime to see how it works. It's important to point out, of course, that if one go to different symmetries, let's say axisymmetric symmetries, these two constraints are very complicated. So as a first approach, we considered the spherically symmetric case. So just a few words about what kind of object can be described by this line element. If this B function here vanishes, then we have a horizon in the spacetime. So we can have a black hole, for example, a black bounce. Also, we can have an object immersed in a cosmological scenario where you can have, for example, the cosmological horizons and so on. Well, if this A function here vanishes, we have infinite redshift surfaces, and this kind of object of line element can also describe a wormhole. If we take this change of coordinate here, it's easier to see this. With this change of coordinate, we obtain the well-known Morris-Thorne line element. And if this phi function here is finite everywhere, we don't have singularities or horizons in the wormhole spacetime. And if this condition, the second condition here is satisfied, we have a throat, and indeed it is a wormhole. Okay, so this is the general kinds of objects that we will investigate. Okay, so let us move to the real problem. We want to consider the most studied VAV configurations people use it to analyze in the literature. And we will see if basically the compact object solutions generated via these non-zero vacuum expectation values are or not self-consistent within this bubble B framework. Later, I will show this for the Calvi-Ramon framework. With this non-zero VAV, we can, the constraint becomes basically this equation here. The constraint, by constraint, I mean the Lorentz violating field equations that, since the field strength vanishes, becomes this relation between the non-zero VAV for the bubble B field and the Ricci tensor. Okay, so just to mention, this non-zero VAV was considered in black hole scenarios, with cosmological constants, in wormhole scenarios, and also in compact star scenarios. So let us see here if this compact objects predicted, like not predicted by, sorry, this compact object reported in these papers here are or are not self-consistent. Okay, so to check the first scenario where we are talking about black holes, we can consider that omega function a constant. With this constant here, with the constraint becomes this equation. And here we have two choices. or the self-interaction potential extremizes at the Webb state, or it not extremizes, say it's a linear function. If it extremizes at the Webb state, then the constraint becomes this equation, and as we can see, the only redshift function that can satisfy this constraint is a Schwarzschild-like redshift function. So if you think of finding a Heiser-Nordstrom black hole, let's say, in the context of Einstein bubble B, using using these VEV, you will not find any Heiser-Nordstrom black hole in this case, because the only redshift function possible and viable is the one that satisfies this relation here. So it's a Schwarzschild-like redshift function. And indeed, in the paper by Kazana et al., they found a black hole solution with this kind of redshift function. It's very similar to the Schwarzschild black hole. Well, if the effective potential is linear, then the constraint becomes this equation, and the only redshift function that can satisfy this constraint is given by this expression that is Kotler-like redshift function. And again, in this paper here, the authors found a compact object, a black hole in a cosmological scenario that satisfies this constraint, okay? The problem appears here in the wormhole case. When we consider, let's say, the Morris Thorne-like element, the constraint becomes this huge equation here. And for simplicity, if we look for tideless configurations, basically when this redshift function A here is equal to 1, so this phi is 0, this constraint equation becomes just this expression here. If we consider the case where the effective potential, where the self-interaction potential surmises at the Webb state, let's say a quadratic one, similar to the considered in that paper from Ovgun et al. We see that the constraint becomes this, and as we can see, the shape function is linear in R. But if the shape function is linear in R, the condition for the existence of a float cannot hold. So in this case, when the self-interaction potential extremizes at the Webb state, and we are considering the non-zero vacuum expectation value that I showed before, tideless wormhole configurations are prohibited. So the solution reported in that paper is not self-consistent in this paper here. So we have to find consistent solutions of wormhole consistent solutions in this Einstein bubble B frameworks. Fortunately, there is a way to do it. If we consider, let's say, a linear potential, the constraint becomes this one. And with this, we have this shape function here that satisfies the constraint. With this shape function, we can have floats and have a wormhole, a self-consistent wormhole within the Einstein bubble B model. There is another way to do it. there's another way to find tideless compact objects within the Einstein bubble-B scenario, and it is based in what I said before, basically by considering that matter and the bubble-B field have a non-trivial coupling. So if matter and bubble-B are coupled, the constraint equation, basically the equation for the bubble-B field, will have an additional term, and this additional term can deal with this prohibition, and even in the case where the VEV, in the case where the self-interaction potential is remised at the VEV state, we can find self-consistent wormhole configurations. We did it in a recent paper, and it works very well. Actually, we found that by doing this, considering a scalar field coupled to the bubble-B field, we find an Ellis-Bronikov-like wormhole. So it's very similar to the Ellis-Bronikov, super simple, but with an additional term that depends on the Lorentz violation parameter. And by vanishing this Lorentz violation parameter, we obtain the standard Ellis-Bronikov wormhole. Okay, so just to mention, in this case here, where the self-interaction potential is linear, the area radius has this dependence here, so it's indeed has a minimum. But as you can see, it's not an Ellis-Bronikov wormhole. It has a different structure. Okay, so now let's consider the same approach for the antisymmetric Hang-Chu tensor. And in this case, the most studied VEV is given by this expression that again has a vanishing field strength. And with this vanishing field strength, one obtains this constraint equation here. This type of VEV was considered several times in the literature. I think the first was performed in this paper here, where they trying to find a black hole using the Kalbi-Hammond field. But later in other papers trying to find black holes and wormholes, they also use this type of VEV configuration. Okay, so let's see if these compact objects are or not self-consistent within the Kalbi-Hammond theories. So again, first we consider the case where omega is constant. When this happens, the constraint becomes this equation. And considering that the self-interaction potential is remised at the VEV state, we obtain that the redshift function that satisfies the constraint is given by this equation. Gamma is a complicated parameter that depends on the coupling constants, but if we can find interesting gamma values that are associated with standard redshift functions. Well, of course, a general gamma is not that relevant because it changes a lot the redshift function, and to model it with reasonable source, it's difficult. So here we will focus only in the case where we obtain a Schwarzschild redshift function, and that basically is when it's Q3 is equals 0, and we have gamma equal -1. In this case, for the self-interaction potential vanishing, we in this paper here of from 2023, the authors found a black hole that satisfy this constraint. And in 2024, other authors found this different line element that also satisfy this constraint. It's important to point out that in this paper here, in this JCAP, the authors say that this solution is different from this one. This is not true. It's just a matter of change of coordinates. It's not that difficult to show that this space-time is the same as this one. The point is that, for here you see this term here, right? So the usual term that appears when you go far from the black hole one in the Schwarzschild case, here is a different constant. So as you can imagine, there is a topological defect in this space-time, and people could think, okay, so in this space-time we have a topological defect, and in this case we don't have it, but you also have this type of topological defect here. You can introduce this constant here in this R coordinate, and it will appear in a new coordinate here in the spherical sector, and with this you have a topological defect in the space-time. So both line elements describe the same space-time, a black hole with a topological defect, and this topological defect is induced by the Lorentz violating fields. Okay, so but the first black hole solutions in Kalbi-Ramond, considering a Kalbi-Ramond field, is not a self-consistent solution. If you look their paper, the redshift function they found has this form here, and as you can see, it cannot match this type of redshift function. Therefore, it cannot satisfy this constraint. So this solution here, even though satisfy the Einstein field equations, do not satisfy the Kalbi-Ramond field equation, and therefore it's not a consistent solution of the model. For the black okay, so here we also consider the linear self-interaction potential. In this case, the constraint has this additional term, and people could find in these two papers here black holes with cosmological constants that satisfy this constraint. Again, the authors say that this line element describes a different black hole from this one, but it's not true. They are the same black hole. It's just a change of coordinates. Okay, for the wormholes in the Einstein Kalbi-Ramond model, the description is very similar. Again, if we consider a self-interaction potential that extremizes at the Webb state, the existence of wormholes is prohibited. Of course, if we are considered tideless wormholes. If we are considering general wormholes with different redshift functions, you can find wormholes, but the point is that it's a numerical work. We cannot find an analytical expression for these redshift functions. And since we are not considering the Einstein field equations and the matter field equations, we are just assuming that these equations are satisfied. We choosing do not attack this problem with numerical tools, because we could biased our approach. So since we are not considering a specific matter source or the full field equations, to justify the numerical approach is very difficult. So we choose just to attack the problem with analytical tools. Okay. But if we consider the linear self-interaction potential, tideless wormholes are again allowed, and they are given by this shape function here. Okay, it's important to say that when this coupling constant here vanishes, the constraint is automatically satisfied for the vanishing self-interaction potential that extremizes at the VAV state, since this right-hand side is 0 and the left-hand side will trivially be 0. So in this case, where we have the Calbi-Ramon coupled solely to the Riemann tensor, tideless wormholes are self-consistent, and any tideless wormhole will be. So any shape function that satisfy the Einstein field equations will be a self-consistent, will correspond to a self-consistent tideless wormhole in this case. So this is let's say, a suitable framework to find tideless wormholes in Lorentz violating scenarios. And indeed, people found a wormhole in this scenario years ago, but this solution is not an Ellis-Bronikov wormhole. It's a different type. It has a different shape function. Okay, so just to conclude, this work gets simple. I believe it's important because there were several compact objects or reported compact objects in Lorentz violating literature that are not self-consistent within these models. So it's important to show that there is a correct way to solve the equations and to find the correct compact objects. And as I said, these constraints, instead of help us, they prohibit several compact objects in Lorentz violating fields. But there's a way to circumvent this issue, and it is considering that the Lorentz violating fields couple to matter. If we do this, then we can find mild constraints, and with this we can find another instances of compact objects that are self-consistent within these Lorentz violating models. Okay, so that's all. Thank you very much.
Thank you so much, Renan. Are there questions here in the room or online? Well, I have many questions. I will ask only a few. First thing, you're working in the metric formalism, right?
Yes, yes.
Do you expect any big difference if you work in the Palatini approach?
Of course. I started looking for these constraints in the Palatini approach, but the equations are very complicated and they are cumbersome. So I have more time to show you the differences, but of course there will be differences. I don't believe the constraints will be the same. I mean, I don't expect that only Schwarzschild-like redshift functions will be allowed in the Palatine, because there we have more freedom.
Okay. One more thing. Yes. Regarding the global approach, you are trying to solve the equations self-consistently. Okay.
Mhm.
And this means that you are not treating the Lorentz violating fields, the Bumblebee and the Cav-Ramon, as perturbations, but you want them to generate the geometry.
Yes.
So this is conceptually different because usually one puts a background solution and then studies perturbations, but you are trying to do it self-consistent. Okay? So is this in agreement with the other authors in general have done in the literature?
Yeah. Basically, we did the same as the authors did before. So we consider the same approach. But indeed, if we consider that these fields are fluctuating or something like this will of course change, because in this case the left-hand side of these equations will not vanish and the constraints will be different. Actually, it will not be a constraint, let's say, it will just a evolution equation.
Yeah, and now just to finish any question. Yeah, there is another question. So,
Did you try to do that in lower dimension?
And lower dimension, not yet. Not yet.
Okay. What about 5 dimensions?
I guess.
No, just 4 dimensions.
Just four,
Just
okay.
4 Sorry?
He's thinking, so you should do it.
Yes, of course.
Okay, yes, I wanted to hear your opinion about the observable effects that this general framework, not the particular solutions, in general, what would you expect if this kind of fields were actually playing a role in nature? What kind of observable effects this could have? I don't know, maybe in
For example, in there is a paper from I think 2019 or 20, I don't know, about the effects of the bumblebee field in gravitational waves. Basically, it changes the number of polarizations. So using a future gravitational wave detector, we could find different polarizations, and it could direct us through some of these Lorentz violating models. But as I said, for example, in these particular models, we can see a peculiar behavior associated with a topological defect. Basically, the equatorial plane has a cone structure. So since we have this topological defect associated with a cone angle, the shadows for sure will be different, because the light rays will behave differently even far from the object.
Okay. So this deficit angle, right?
Yeah, exactly.
Okay. Anyway, so I would like to ask more questions, but we are already late and we have 2 more speakers. So thank you again, Renan.
Thank you.
Okay, so and now it's the time for Anderson. Anderson, if you want, you can share your slides.
Okay, so I guess you can hear me clearly.
Yeah, the sound is perfect. The video is also good. And let me introduce Anderson. Yeah, Anderson is a graduate student. He started the master for Nestor. You are not the youngest here. Oh, that's now
category. Okay? This is the youngest in this business. And he did this work at the Federal University of Ceará in Fortaleza, Brazil. And this is his final degree project, basically. Okay. So Anderson, please, you can start whenever you're ready.
Okay, so good afternoon. My name is Anderson Bragado. Professor Gonçalo already introduced me. And I'm going to discuss about periodic equatorial orbits in a black bounce scenario. So basically, the content of this presentation is based on this work that I developed together with Professor Gonçalo, and it was recently accepted for publication just a few weeks ago. So, giving just a brief outline of what we're going to discuss, we're going to start by establishing a classification scheme for basically any closed orbit around a static spherically symmetric spacetime. And in those cases, it will be possible to associate with each orbit a triplet of integers, and with these three integers, then construct a rational number. And in fact, this rational number, despite this apparently artificial way of constructing it, will have a physical significance, a very simple one. And with this taxonomy scheme, we will then apply it to say how it can be applied to the Schwarzschild and Kerr metrics. And we'll see that the rational number will have some peculiar characteristics, and with the knowledge that we will construct in this case, it will then be possible to bring in some analogies with a black bounce model, which is the Simpson-Visser model, and its rotation version, analogous to the Kerr metric. Okay, so if we were to discuss this classification in a more simple scenario, for instance, in Newtonian orbits, the job will be much simpler because we already know that we could have elliptical orbits or hyperbolical orbits or parabolical ones. But when it comes to general relativity, things get a little bit more complicated, and this simple way of seeing it is not valid anymore. Because of that, we have to introduce this classification scheme. So, okay, this prescription was given by this paper, a periodic table for black hole orbits, is a main reference that we use in this work. And in that work, they basically discuss this classification and apply to the Schwarzschild metric and the Kerr metric. So, okay, so starting, if we're going to see some examples of orbits in Schwarzschild metric, that would be some of them. So remember that we want to associate to each of them three integer numbers. So first integer, that is very easy to see, is the number of leaves. For instance, so here I have a 3-leaf orbit, a 3-leaf orbit, a 1-leaf orbit. And those below looks like versions of the upper ones, but with some precession in there. And in fact, these precessions can are actually a closed orbit, but with many leaves. In this case, around 1,000 leaves that makes them have this appearance. So, okay, this is the first integer, the number of leaves, and this is another example of a 2-leaf orbit. But in fact, this is not the unique 2-leaf orbit that exists. And actually, the trajectory could initiate from the apastron, go to the periastron, and then before going out to the apastron again, execute additional 1 real V or 2 or 3 or 4 without breaking any symmetry. So in fact, this is the second integer. And this is an example of a 2-leaf orbit, but with 1 wheel. And then we already quickly introduce 2 integers that we are going to use to classify. So we have to talk about the third one. So one could say, so these are not unique 2-leaf orbits. We have another feature in them. and u would be wrong. In fact, these two integers will describe exhaustively these cases of two leaf orbits. We have to increase the number of leaves to see the other integer. So going to a three-leaf orbit. So if you have n leaves, we can then associate this orbit any vertex polygon. And then we could label these vertices going from 0 to n minus 1. So in this case, we have 3, 0, 1, and 2. And in fact, an orbit could come from the apastron, then approach the periastron, and then when it goes out, it could go out to the apastron label as 1 or the one label as 2. And in fact, these two cases are essentially different. And these would be the three integers that we need to topologically describe entirely these configurations. So in a brief summary, the integers we have are the number of leaves, the number of wheels it executes before going to the apastron, before going to the periastron, and the number of vertices skipped. And actually, these numbers are not fully independent. They depend on each other. So the number of wheels is completely independent, could be any number, but of course, the number of vertices skipped has to be smaller than the number of leaves, because I can't skip more leaves than the leaves I have. But in fact, there is another constraint in it, and it's easy to see with the next example I'm going to show. But it's basically that V and Z cannot share any common factor. They have to be relatively prime because of this thing that I'm going to expose now. So this is two four-leaf orbits with one wheel here and here, and in this case, with V numbers, the number of vertices skipped 1 and this 3. Okay, so these are perfectly adequate orbits. That there's no problem with them. But let's see what would happen if the V number was not 1 or 3, but was 2. Then in this case, the orbit would start from the apastron label as 0, and then approach the periastron, and then, because it skips one orbit, would go to the apastron label as 2. And from this, upon this apastron, would skip the 3, go to 0, and this way successively. And that means from 0 to 2 to 0, from 2 to 0, we don't have anymore a four-leaf orbit, but a two-leaf orbit. And this accounts for a kind of repetition we have in these labels if we do not consider that these numbers have to be relatively prime. This problem will happen always when this happens. That's why we impose this other restriction. And in fact, because of this restriction, it is possible to construct uniquely a rational number, because we know that a rational could be uniquely described as its integer part and plus its fractional part. And it's unique if we consider that these numbers, integer numbers in the fraction, to be relatively prime. And this is just what we have here. So in this way, I can construct a rational number, and to every orbit, I could associate a rational number to it. And then this is a classification scheme. So it looks a bit artificial, but in fact, this rational number has a significant physical significance. For instance, it can be shown. I'm not going to discuss it very fully, but if you consider the angle that's swept by the radius vector from the apastron until the periastron, or from the apastron to the other apastron, never. It's the same thing, just multiplied by 2. You could find a relation between this angle and this rational number that we've constructed. And in fact, this is a very important relation, because it's with that relation that we can construct our orbits and determine what classification our orbit has. Of course, if we can't, and determine very clearly how many leaves it has, or maybe it's not completed its full period yet, but it's an important relation. So, okay, with this, we can discuss then how this classification is applied to the Schwarzschild and Kerr metrics. So let's go. In the Schwarzschild case, we know that we can write the radial equation as just as we have a conservation of energy in usual Newtonian mechanics, but with this effective potential that depends only on the angular momentum L. So in fact, we can now analyze how each orbit will look like only by having a look in the effective potential. Then we broadly can describe how the orbits would behave. So this is a figure that shows the effective potential for diverse values of angular momentum. So for the cases where closed orbits actually exist, we'll always have these maximums that are associated with unstable circular orbits and those minima that are associated with stable circular orbits. So I didn't talk how would one classify circular orbits in that scheme. It's not very clear, but in fact, for the stable circular orbits, they have the same classification, the same association with rational when we consider small perturbations on it. But of course, these perturbations can't be done in the case of the unstable circular orbits. In those cases, we have more complicated, but anyway, it's simple. It's just different because now we have to associate to them an homoclinic orbit, which is an orbit that initiates from, say, some finite aperture, then approach this maximum indefinitely, executing potentially infinite wheels. And because it executes infinite many wheels, it will have associated to it a rational number equals infinity. So we have no bound at all. And this is important because as we increase the angular momentum, this maximum starts to increase. And when it is unbounded, meaning greater than the value it has in infinity, then the importance for our classification scheme means that for this range of energies that we have here, the rational number associated to the orbits will start to have upper bound. So this case here, or what this happens, is what we call the IBCO, innermost bound circular orbit. And this is the importance. So if we have L greater than IBCO, the rational number starts to have upper bound. And if not, it have no bound. The lower bound that will be always determined by the rational number associated to the stable circular orbit. And of course, the angular momentum has to be greater than the I-COOP. The I-COOP is referenced by this orbit is the innermost stable circular orbit. It has some importance and it's very interesting in some aspects, but for our case, just means that it's the minimum value that we can need to close orbits to exist. So, okay, moving forward, as I was saying, if we are not close to the maximum, the orbit will not execute many wheels. So in this case, we have, and to this energy and this effective potential, this value of angular momentum, we have actually for orbits with no wheel. But if you have one wheel, then it must be the case that this value of energy is very close to the maximum. So it can execute many wheels. So it's a strong field case. So, okay. And another very interesting aspect of this rational number is that it increases monotonically with the energy. And this is also very important for our computational analysis because because of this feature, we can in fact think in an algorithm to determine the actual associated rational to each orbit. This is discussed better in the paper. And of course, energy is not a direct observable that we have in astrophysical terms. So if you prefer, you can exchange energy for eccentricity. So the associated integer number also increases monotonically with eccentricity. So, okay, these are the main features of this rational number that I want to discuss. Then we can now bring in this knowledge to make some analogies with the Simpson and Visser model. So this is the line element presented by Simpson and Visser. It is basically the Simpson-Visser metric, but the Schwarzschild metric, but where we had R, we exchanged by square root of R squared plus R mean squared. And this R mean is just a parameter that we can control. And depending of the value of this parameter, this line element could describe a Schwarzschild black hole if R mean 0, or a regular black hole, or a wormhole. That's why it's so interesting. So, okay, if we derive the equations of motion, we find the angular equation and the radial equation, and perhaps for surprise of no one, they are just like the equations of motion for the Schwarzschild metric, but where I had R, I exchanged with square root of R squared plus R mean squared. So, but what is interesting? Remember that the effective potential for this classification scheme is very important. So, and for analyzing it, we can make some broad conclusions about the aspect of each orbit. So this figure shows an evolution of this effective potential as we increase this parameter called mean. We see that as it increases, it is shifted to the left, and this is the continuation of this evolution. And in fact, looking to this plots, we could determine ranges of our mean that have some different features. And I'm not going to discuss it, but it is discussed better in the paper. So, okay. And perhaps the most important part is when we remember of the relation between the rational number and the angle swept by the radial vector to the aperture to the other aperture approach, or coming from the aperture to the Bergastrom, doesn't matter. So this would be the calculation of this angle for the Schwarzschild case. Very direct to see, but we can show its basic algebra. It's very easy to show that in the Simpson-Visser case, this angle will be transformed by this, which looks pretty much like the Schwarzschild case, but with this kernel inside the integral. And it can be seen that this kernel is always greater than 1. And because of this, what increasing R mean causes in the orbit is that this accumulated angle increases. But remember that this accumulated angle is related with the rational number, which is directly connected with the topological aspects of the orbits. So it means that the rational number increases, and the integer part of the rational number, the number of wheels, and the fractional part, that fraction between the number of vertices skipped and the number of leaves. And what this means in practice when we look to the orbit is that as we increase our mean for the same initial condition, of course, the orbits start to precess. And this is an observable effect. You could say that is kind of subtle, but in fact, if we are in very strong field regimes, small change in mean could cause a very prominent change. For instance, causing a 3-leaf orbit to become a 2-leaf orbit. So also, this is just to showed in the paper a case where the metric already describes a wormhole, and you can see also that they are not very distinguishable by sight, just by eye, but in fact they have completely different equations of motion, but because they have this same classification, same initial conditions, they look very similar to them. So just by seeing it, if you don't have enough precision, you could not determine which is which. We were in the Crashfield case or in Simpson-Visser case, and inside the wormhole case, I was discussing only when the cases where the trajectory don't actually enter in, don't actually traverse. So if we now discuss traversing orbits, we have to make a little adaptation in this prescription of the rational number. And in fact, it's very simple. It's basically that the actual observed topological aspect of the orbit would be equivalent to our observed rational number that is given by basically the rational number calculated with the angle plus the fractional part. It can be shown, of course, assuming that you can see what is happening when the particle traverses and it comes to the other side of the wormhole. So I could discuss a little bit more about this, but I'm just going to move forward. And looking to the effect potential, I say it's very important. We can also note that it has two very distinct regions, which is this inner region, an object could traverse the wormhole by by being bounded by these maximums, or could be by not being bounded by those maximums, but by these outer orbits. And a very distinctive characteristic of each one of those is that, of course, these inner orbits have very small eccentricities. But other than this, in fact, this inner orbit, they still respect that relation that I spoke of just now, that the associated rational number increases monotonically with energy, but those outer orbits are just the opposite. They decrease monotonically with the energy. This can be understood because of those maximums and homoclinic orbits and etc. But it's a very interesting aspect of noting it. So these are some examples of those inner orbits. As I said, they have very small eccentricities, and this example is an example of an outer orbit. So okay, this is pretty much the overall of the analysis in the Simpson-Visser metric. I think now we can move on to the Simpson-Visser model, now adding rotation to it. So what would the line element look like? And this is it. You can use some prescriptions like the Newman-Jennings algorithm or on any other prescription to derive this, but perhaps not surprisingly, this line element is just the Kerr metric, but exchanging where we had r by square root of r squared plus r mean squared without changing the differential. So it's not just a coordinate transformation. So also like the Simpson-Visser model without rotation, it can describe just a Kerr metric or a regular black hole or a wormhole, depending of the combination of this value of the parameter R mean and the spin parameter. So, and also analogous to the Kerr case, where we cannot describe the orbit by an effective potential. Actually could, but the effective potential, what we would call the effective potential, would have energy in it. So it's a very odd thing to call effective potential. But in fact, we can derive the equations of motion in a normal manner, Jacobi prescription. We suppose the solution separable, and then with some calculation, we would find these equations of motion that are completely analogous to the Kerr case. And as the Kerr case, besides not having this effect potential, is described by pretty much the same features as the Schwarzschild case, the rotation Simpson-Visser case is completely analogous to the normal, without rotation, Simpson-Visser model. So, for instance, I would say that this set of equations are not the most adequate to computational simulations because of this plus and minuses. So at turning points, we had always to exchange the plus with a minus, and this always carries a little bit of error unless we put a lot of precision at turning points, and so it has some computational expense. So it's more intelligent to use Hamiltonian approach, and it's have a smarter way of constructing it. With this Hamiltonian and the Hamilton equations, we could derive those equations. And it would seem that now we lose because we have more equations, but in fact, we don't have to solve all of them. And now we don't have anymore the problem of the turning points, so it's a very better approach. So okay, as I was saying, we have the same features as we increase our mean. What we see is that the associated rational must increase, and with this increasing, we see the orbits start to process. And also, we could have also more prominent changes, like transforming a 5-leaf orbit into 4-leaf orbit and a 3-leaf orbit, and that's successfully. And also, we also have the wormhole case, but perhaps the most different aspect is that, of course, there are co-rotating orbits and counter-rotating orbits, and they are essentially different because of the frame dragging. And as I said in the Simpson-Visser section, there are some ranges of our mean which carry some different aspects. So this figure is showing in the paper just that it can happen that the prograde orbits are in some range of this Arminian spin parameter, while the retrograde orbits are in another, just that. So I hope I could briefly outline and adequately explain this geometrical approach to analyze orbits, closed orbits around spherically symmetric metrics like the Schwarzschild metrics and Simpson-Visser metric. Also, I could say that I was only dealing with equatorial orbits, but there is actually a similar prescription of this classification for non-equatorial orbits that are a little bit more complicated, and it was done by the same persons of that paper that I cited, a periodic table for black hole orbits. And also, it's very important because other than this geometrical importance and theoretical importance, it can have some analogies with another models, like some cases, the evolution of pulsar stars, you have the rising of some black bounce with some parameter I mean that can evolve with accretion of matter, and this internal change in the model could be seen then analyzing the evolution of those orbits around it. So it have some observable importance. So this is what I wanted to say, and this is the main references that I use to make this work. Thank you.
Thank you. We have time for some brief questions. Any comment?
maybe Anderson, you could explain quickly how to compute these periodic orbits, because it's not trivial to choose the energy and the angular momentum to obtain one of these orbits.
So the most important part of it is that this rational number increases monotonically with energy. So suppose we have to choose one of them. So suppose we fix some value of angular momentum. So okay, then we know the limits of the energy. So we know that the lower limit is the stable circular orbit, and the upper limit is the unstable circular orbit, or perhaps the value it has at infinity. It can be both. Okay. So in that case, we only use the bifurcation method. So for instance, we want to find 3-leaf orbit with one wheel and the number v associated with 1, the number of vertices skipped 1. So we compute the rational number that we want, and then we make this range, and we use bifurcation method, which is we have this range. Then we guess what would be the orbit at the middle of this range with the half of the energy, and then we compute the rational number. Then we see, oh, it's greater than the rational number I want. So I want to be I rename the range. So if it's greater, then it means that the actual number I want is near here. So if it is here and I guess one of here, then I rename and I cut in half again. And when I cut in half again, I calculate again. Oh, now it's lower. Then we have another range, and then we do this successively until it converges to some wanted precision we have. And of course, and we determine the value of this rational number using that expression that I think is the Simpson section. This is rotation. Of course, we can put using this expression, this integral. We numerically compute this integral.
Okay, thank you. So any other question or comment online or here? No? If no, then let's thank Anderson again. Give me a second to do this, and the session expires and we need to extend the session. We're a bit late. Okay, so we still have one speaker today, and is Payal Sarkar. She's from the University of Cape Town in South Africa. So, Payal, since I don't know much about you, could you please introduce yourself a little bit, just to mention when you did your PhD or what you're doing? Okay. Thank you.
So, hi everyone. I have I have completed my PhD from Birla Institute of Technology, India, and then I have I did my first postdoc from India, and after that I have joined at University of Cape Town. So I have joined recently, mainly 2 weeks back, and I'm working in Gravity Cosmology group here with Professor Alvaro and Peter Tansberg.
Thank you so much. So whenever you want, you can share your screen and start.
Yes. Yeah. So can you see?
Yes, we can see.
Okay. So today I will discuss inflationary cosmology with scalar curvature mixing term half xi or phi square. So before starting my talk, I will discuss why we need this modified gravity. So the the picture here basically shows the component of our universe, and we can see that the 5%, our universe is composed of a matter which is ordinary matter, which is takes the 5%, but other 95% are composed of dark matter and dark energy, and those two components are still unknown in we know from current observation that our universe is expanding, and in order to explain this expansion, we need dark matter and dark energy. Those are not experimentally found so far. So people have modified the gravity in a hope that maybe the modifications or can produce some kind of dark energy and dark matter. This is the main motivation for doing modified gravity. And in this talk, I will also discuss inflation. So inflation is the exponential expansion of our universe, which is basically in early times, at the beginning of a universe. And in order to describe the inflation, I will take the simplest model, that is the scalar field model. Now, in literatures, we have various kind of scalar field potentials that can describe inflations, but those models can have some problem. They have produced the very high value of tensor to scalar ratio, which are actually cancelled by our recent observational data. That's why I have considered non-minimal coupling. So in this talk, we want to see whether this non-minimal coupling, addition of this non-minimal coupling can create a desirable observational data, which we can match from recent observation. So for this non-minimal coupling model, so we have our model looks like this. So the first equation is the action in the Jordan frame, and so the last term you can see is the non-minimal coupling term between the gravity R and the scalar field phi. So this action is a little bit of complicated. So in order to make this action in a simpler form, I have performed the conformal transformation of the metric, as you can see. So the omega is the conformal transformation parameter, which includes the information of the non-minimal coupling parameter xi. And after performing this transformation, we will go to a new type of frame, which is known as Einstein frame. So in Einstein frame, the coupling term is not present in the action, but the parameters like the Ricci scalar or the Hubble or the scalar field, every parameter will be transformed in such a way that they will include the information of the non-minimal coupling term. So in the action, we can see the our scalar factor, potential, everything is transformed. That's why there is a cap term in the Einstein frame. So in this new transformed parameters, they contain all the information of the non-minimal coupling. And if we take if we do the calculation in Einstein frame, our Einstein equation will be same as the Einstein's equation in GR, but in transformed parameters, like you can see from the equation 3. And this equation is we will get after applying the slow roll approximation. And the last one equation is the transform ion energy momentum tensor in Einstein frame. So since we are considering the slow roll conditions, so slow roll condition is the scalar field phi. We have assumed that the scalar field phi moves slowly for a sufficient long time over a flat potential. This condition is known as slow roll condition. And in order to explain this condition, we need two type of parameters. So these are known as slow roll parameters that can be described either in terms of potential or in terms of Hubble. In this paper, we have considered the potential slow roll parameters. Those are epsilon b and eta v, and all are in Einstein frame. That's why there is a cap term. So epsilon b cap and eta v cap. And these are expressions, and the CMB are observable, which is known as NSR and NT, which are basically scalar spectral index, tensor to scalar ratio, and the tensor spectral index. Those value we can get from the Planck observational data, and those expressions or those observables can be expressed in terms of the slow roll parameters also, that I have shown in the equation 2. We also have calculated the non-Gaussianity parameters, which can be written in terms of the Schroeder parameters. So in the main paper, we also have calculated the non-Gaussianity parameter for the higher orders also, like for FNL is basically the linear order non-Gaussianity parameter, but in higher order also it is mentioned in the paper. So now, in order to describe the inflation, we have considered here different type of potentials. So the first potential is a combination of the power law and the exponential one. The single power law or single exponential potential is already discussed in many literatures, and people have found that those type of potentials cannot produce either good E-fold or their tensor to scalar ratio is very high. That's why we have combined these two type of potentials, and we want to see by combining these two potentials whether we can get results or not, good results or not. So from the left plot is for the xi equals to 10 to the power minus 3, and the right plot is for xi equals to 10 to the power minus 4. Xi is basically the non-minimal coupling parameters. And we have considered lambda value is 0, 0.1 and 0.15, and p equals to 2 and 4. And if we see that if we take only phi square or phi to the power 4 potentials, then we can see that our values are matching with the 68% of the WMAP data for n equals to 50 and 60. But if we include non-zero value of lambda as well as non-zero value of p, then we can get that our values of our NS and R values are matching with the Planck data, the central green and the other colors. So those are the basically Planck one. So we are matching with the Planck data for n equals to 50 and 60. Sorry. Yeah, so this is the next potential. Next potential is a combination of the hilltop and the exponential one. And here also the single hilltop and single exponential potential cannot produce a good E-fold. That's why we have combined these two type of potentials. And in this case also the left plot is for xi equals to 10 to the power minus 4 and xi equals to 10 to the power minus 3, and the right plot is for xi equals to 10 to the power minus 4. And here also we can see that if we take only lambda equals to 0 and p equals to 2 or 4, then we can see that our n equals to our ns and r values are going beyond WMAP also. Like you can see for the black points, at least for n equals to 50 and 60. But if we take the non-zero value of lambda and p, then our values are within the WMAP 68% data. And few cases it is matching with the Planck data also. So from these two cases, we can see that by combination of these two potentials is exactly better than the previous assumption that about the previous work that people have done so far. And the third case is a third and fourth potential at the mostly the fractional one, and the left one is for the V naught into 1 minus lambda phi to the power p, and the right one is for the fractional one. And we can see that in each cases we are getting a good result. But if we can see the right hand side plot, we can see this plot is exactly the actually matches the NS and R quite good compared to other three cases. So in this case, we can see we're getting the NS and R, which are at least R value is the smallest one, and NS value is matching at the plus minus 3 sigma of the Planck data for n equal for E-fold number 50 and 60. Now, if we consider the minimal gravity case, like if we take the xi equals to 0, then we can see that for each cases, either we are getting NS value which is beyond Planck, or R value we are getting quite high, except for case 4. In case 4, we are getting NS and R almost equal to the non-minimal gravity case. Like in non-minimal and minimal gravity, this case 4, we are getting almost equivalent. So for case 4, we can see that xi value is not playing the important role, but the other three cases, we can see that including the xi value or including the non-minimal coupling gravity results. We also have calculated the non-Gaussianity. So non-Gaussianity, and we can see that in first two plots are for potential 1 and 2, and the lower two plots are for potential 3 and 4. And in each cases, we can see that our data is of the order of 10 to the power minus 2, and at least for n equals to 50 and 60. So that during the inflationary period, our non-Gaussianity parameter value of the non-Gaussianity parameter is very low, which is we know that in order to describe the inflations, we know that our perturbation plot should be the Gaussian one. So hence the non-Gaussianity should be very small, and this is what exactly we are getting in these cases. And if we see the higher order non-Gaussianity, those are much more smaller. And we also see that if we take the higher value of phi, the scalar field, then our higher order non-Gaussianity almost tends to 1. So that almost tends to 0. So there is no higher order non-Gaussianity term. So let me summarize that. So in this work, we have introduced a non-minimal coupling term between the gravity and the scalar field phi, and we have considered 4 different type of models which can predict our NS and R, which we are getting from Planck and WMAP data. And we have compared our results with the previous studies, and we have found that the value of xi that we are considering is 10 to the power minus 3 and 10 to the power minus 4. Those are comparable with the previous studies. And those values of xi is actually get the best results for the for observations. And we have found that in case 4, which is the potential, the fractional one, is fits best for our non-minimal framework, as well as in minimal scenario also, which can explain the inflation. And thank you. Thank you.
Thank you so much, Payal. Any questions? Yes, there is a question here.
I can speak there.
Try to speak to see if she can hear you.
Okay, I'm just wondering, when you say compared to Planck, are you referring to the value that you're predicting from your model being matching that of the lambda CDM predicted Planck results, or what are you comparing here exactly with that?
Yeah, so lambda CDM model we have not considered, since our potentials is quite different. And but we have compared those, we have taken those potentials, and we have calculated our results in case of minimal gravity. So lambda CDM we have not considered in this case, since we are focusing the normal coupling term only.
Okay, but then my follow-up question, the Planck values for lambda CDM, that's model dependent answers. So aren't you now you're taking a completely different model on the Planck data and saying, oh, because this model just happens to be the same value as what this other model that's also dependent, a model dependent answer, isn't that kind of you're comparing two different things to each other? Because the model itself changes the value of the C and B base fits, because you are projecting it using the model to fit the spectrum. I don't know if it makes sense. What I'm trying to say.
Yeah, so the observational data, which are basically NS and R, those Planck, if you can see the Planck range, so those basically values are important to describe inflations for, I think this is important for any case of model. Like if you are taking some model, and if you are matching that our NS and R is exactly lying in this observational range of the Planck, then we can see that our value produces the results which are matching with observations. So that is what we're doing in this case. Like we just calculated our NS and R using our model, and we have matched that, and we are matching our NS and R with the observations, whether it is lying in the ±3 sigma range or not. That's what we have done. And also the R value is nowadays is very decreasing. Like current observations, if you can see, R value is less than 0.3 or something. So sorry, 0.03 or something. So that's what I'm just taking. Like if R value is less and NS value is lies within this range, then we are getting a model. Our model can produce explain inflation.
Okay. Okay, any other questions or comments? If not, thank you again, Fire.
Thank you so much.
Thank you everyone for participating in this session. Okay, tomorrow we will have one more session, and hope to see you here. Okay, have a good day, afternoon, or whatever is in your time zone. Okay, bye bye.
Thank you. Bye.